This is lecture 4 of the course Engineering Mechanics. In this lecture, we are going to learn about a special kind of coordinate system. The name of this coordinate system is the path coordinate system. In this coordinate system, we have three basis unit vectors. These unit vectors are mutually perpendicular and the notation of these three unit vectors are as shown here on the slide. The first unit vector is called the tangent unit vector. We denote that unit vector using this symbol E hat subscript t. Note that this subscript t is representing, or it stands for, the word tangent. This t should not be confused with the time, the symbol for the time variable, which for example is appearing here. So this t is time. However, when a t is appearing with a unit vector as a subscript, that is not time, but it represents the word tangent. The second unit vector of the path coordinate system is the normal unit vector, and we use the symbol E hat subscript n. The third unit vector is called the binormal unit vector, and we use the symbol E hat subscript b to denote that. Now the definition of the binormal unit vector is what is shown here on the slide. It is the cross product of ET with EN in that order. The next question is, what are the definitions of the tangent unit vector and the normal unit vector? To describe these two vectors, I refer to the figure shown on the slide. As usual, we have a reference frame F. We have an observer who is observing the motion of a particle. That particle is P. This point is the location of the particle at the current time instant t. There is another P on this figure, and this P denotes the same particle, but not at time t, but at a time instant in the past, in the history of that particle. So t reference is a fixed time in the past. So this observer started tracking the motion of the particle at t ref, and he has been monitoring this motion, and at the current time instant the particle is at this location. Now this red curve that is shown here, this is the trajectory of the particle P as observed by this observer. Trajectory, or the path that the particle has taken, particle P has taken during the time t reference and t. In the last lecture, I mentioned that the scalar coordinate of a particle at time t in path coordinate system is this variable s. S is the distance of the current location of the particle measured from the location of the particle at t reference, and this distance has to be measured along the path or the trajectory of the particle itself. Alright. Now coming to the question that I raised earlier, what is ET and what is EN? ET is a unit vector that is tangent to the trajectory of the particle at this current time instant. So the direction of ET is decided by the local tangent to the trajectory at this location. What is EN? EN is a unit vector that is pointing towards the local center of curvature of the trajectory at this current time instant. Indeed, ET and EN are perpendicular to each other. These are the descriptions of ET and EN, and as I mentioned earlier, once you know ET and EN, the binormal vector is obtained by taking a cross product between ET and EN. Now, having defined our unit vectors, our basis unit vectors, and also having defined the scalar coordinate s with which we locate the current position of our particle of interest, now we raise the second question. The second question is, what is the expression for VPF in the path coordinate system? VPF is the velocity of the particle p with respect to the frame in context. Let's derive this expression. Let's try to express VPF in the path coordinate system. In the previous lecture, we focused on the same quantity VPF. We had the same frame F, the same particle we were monitoring, and we derived an expression of VPF first in a frame fixed Cartesian coordinate system. Subsequently, in the last class itself, we also derived the expression of the same vector VPF in cylindrical polar coordinate system. Now it's the time to derive the expression of the same vector in the path coordinate system. The derivation of this expression starts with the very definition of VPF, which is what I have written here. It is the rate of change of the position vector of the particle P measured from a point which has to be fixed in frame F. And that position vector is denoted by RPO here. Now what we are going to do is apply the chain rule of differentiation and write this expression, this derivative, as the product of two derivatives. The first derivative is of the position vector with respect to s, where s is the coordinate of the native coordinate of the path coordinate system. Now this derivative is still with respect to f, means it is the rate of change of the vector RPO with s as observed by our observer fixed to f. And then the second factor that appears is simply ds dt, and s being a scalar, We don't have to put any baggage here like frame F or frame M or any other frame. It is just the time derivative of the scalar. So we get rid of that. We don't have to put anything there additionally. The expression is alternatively written as this, where S dot is just a shorthand notation for the time derivative of ds, time derivative of S. Now let's focus our attention on this particular factor, rate of change of the position vector with respect to S. According to the definition of this quantity, this is a limiting value of the quantity that I have written here. As delta S goes to 0, we need to find the difference between the difference between the position vectors at two locations on the trajectory, and we divide it by the small increment in S, and when the limit goes to 0, delta S goes to 0, we will get this quantity of interest. Now these two vectors, RPO at S plus delta S and RPO at S, have been shown on this diagram. So this is the position at time t. This is P at t, and this is the position of P at t plus delta t. During this time, the particle has traveled an additional distance delta S, and that trajectory is shown in as dashed lines here. So RPO vector is the vector pointing to this location measured from this point or the origin of the reference frame F. Similarly, this vector, the vector pointing to this location measured from O, is our RPO at t plus delta t. Now we realize that RPO at t plus delta t is same as RPO at S plus delta S, and RPO at time t is same as RPO at S. These are just alternate different ways of writing the same vector. So these two vectors are same, these two vectors are same. Coming back to this expression, rate of change of RPO with respect to S, we write this quantity of which we are trying to take the limit, we write that quantity as delta RPO delta S, delta RPO by delta S. And this delta RPO I have shown here on the diagram. This is the delta RPO vector. So this is the particle location at time t, this is the particle location at t plus delta t. So this vector shown as dashed line is the vector delta RPO, which is the difference between this position vector and this position vector. So essentially this is the limit of delta RPO by delta S. Now looking at this geometry, we are going to draw some conclusions. Looking at this trajectory, I present this argument that as delta t goes to 0, which is same as saying that as delta S goes to 0, I present this argument that the magnitude of delta RPO should go to delta S, right? So as delta S becomes 0, this vector, what we are showing here, the length of this vector or this dashed line will become the same as the length of this path that the particle is trying to follow in the limit delta S going to 0. And thus this conclusion that delta RPO magnitude goes to delta S as delta S itself goes to 0. Once we realize this, it is easy to conclude that the limiting value of the magnitude of this vector, is going to be magnitude of delta RPO by delta S, and since the magnitude of delta RPO itself goes to delta S, the overall conclusion is that the magnitude of this vector itself should go to unity. In other words, DRPO, DRPO ds with respect to F must be a unit vector. Okay. Further, I want to present one more argument, and that argument is related to the direction of this vector, direction of delta RPO vector. Looking at this figure, I present the argument that as delta S goes to 0, the direction of delta RPO vector will become more and more like the direction of the local tangent at this location. I repeat, as delta S goes to 0, the direction of this vector, the delta RPO vector, will become more and more aligned to the local tangent vector at this location. This is my second conclusion. As delta S goes to 0, the direction of delta RPO will become direction of ET itself. So earlier I made a conclusion that the magnitude of delta DRPO ds vector should be unity, and now I am saying the direction of delta RPO vector should become the same as direction of ET as delta S goes to 0. But the direction of delta RPO is the same as the direction of, has to be the same as the direction of this, right? The direction of delta RPO has to be the same as the direction of this vector. Why? Because the difference between delta RPO and this whole vector is only, means they differ, these two vectors, delta RPO vector and the whole vector, they differ only in terms of a scalar which is being used to divide delta RPO. Delta S is the scalar. So the direction, whatever direction delta RPO will take, the same direction the entire vector delta RPO by delta S will take. And that is my second conclusion, that the direction of delta RPO by delta XS should be the same as ET. So combining this conclusion and the first conclusion that I made about the magnitude of the vector, the conclusion is that this vector DRPO ds with respect to F should be nothing but the local tangent vector of the trajectory. Once we have this information, then we go back to our expression for VPF. On the previous slide, this is what I got. I processed this expression till this point, and now I am saying that this vector must be simply ET. Thus, VPF, the expression of VPF in the path coordinate system is nothing but S dot ET, the first derivative of S along ET direction. So this is the kind of expression we were looking for. We wanted to express VPF entirely in terms of S or its derivative and one or more of the native unit vectors of the path coordinate system. One or more of the native unit vectors of the path coordinate system. Indeed, ET is one of the native unit vectors of the path coordinate system. So this expression is completely acceptable, and this is how VPF will be calculated if your working coordinate system is path coordinate system. Now the magnitude of VPF is also called the speed of particle P with respect to frame F. Now this is a scalar. Of course, the magnitude of a vector, any vector, is a scalar. So in that way, the speed of a particle is a scalar. But keep in mind that the speed of particle P by itself doesn't mean anything. The speed of particle P is fully defined, is sensibly defined only when you also mention with respect to which frame. The frame in context is also important. So now we have a situation in which we have a scalar, but that scalar, the definition of that scalar is frame dependent. Frame dependent. We have a frame dependent scalar, which is fine. Now this phrase, speed of particle with respect to frame F, is a statement which is actually independent of the coordinate system, right? Because a vector itself is coordinate system independent, so the magnitude is also coordinate system independent. However, if our working coordinate system is the path coordinate system, then the expression for the speed must be the magnitude of s dot et, what we derived here, and that must be the magnitude of s dot, but then it is adequate to write this simply as s dot because s dot is guaranteed to be always greater than or equal to 0. S dot itself is guaranteed to be equal or more than 0. It is a positive definite quantity. So it suffices to write speed of the particle as s dot with respect to frame F here in our context. Moving on, the next agenda item that we have is to be able to write the acceleration of the same particle with respect to this frame F in the path coordinate system. Again, I want to remind ourselves that in the previous class, for the same particle with respect to same frame, we derived an expression for APF first in a frame fixed Cartesian coordinate system. If you go back to the previous video, you will see the full expression there. Further, in the previous class itself, I also derived the full expression of APF in cylindrical polar coordinate system. That expression is also available in the previous video. In this case, in today's class, now we are going to express APF using the path coordinate system as our working coordinate system. So the expected answer is going to have ET, EN, possibly EB, one or more than one of the basis unit vectors of the path coordinate systems, and we also expect maybe S or its derivatives to appear there. We will see what exactly is the form that we end up with. So the starting point towards getting an expression for APF is to take the derivative of VPF with time and with respect to f. Now VPF, we already have obtained the expression of VPF in our path coordinate system, that is s dot et. Now if you differentiate this product, I am going to get two terms. First has s double dot et, and then I have s dot multiplied by the time derivative of et, the tangent derivative, the tangent unit vector with respect to f. Here I am again reminding ourselves that when t is appearing as a subscript to a unit vector, it is that t implies the word tangent and it has nothing to do with time. Whereas this t that is appearing here, this is our independent variable, independently varying time variable mentioned here. So please do not get confused with the appearance of two different types of t in the same expression. Alright, so coming back to this expression, the first term is already well processed. I do not need to do anything additional. However, the second term that I have, I do not want this time derivative to appear here. I want to process it. And with my motive to process it, I am going to again apply chain rule of differentiation and going to write this time derivative as a product of first derivative with respect to s, and then the second factor will come, which is rate of change of s itself, which can be written as s dot, and that s dot I bring it back here and it becomes s dot square. So what I am left to focus on is the derivative of the tangent unit vector with respect to s as seen by our observer fixed to f. Let's process this term now. Now to get an expression for that term, I am going to use some diagrams here and I am going to draw some conclusions based on the geometry included in these diagrams. So let us first focus on this term. Limiting value when delta s goes to 0, magnitude of the difference between the tangent unit vectors at two time instants divided by delta s. You will realize that this is nothing but the magnitude of this vector det ds with respect to f. It's the magnitude of that vector. So like the kind of arguments I presented 5 minutes ago, I am going to get an expression for this term in two steps. I'm going to get an expression for this derivative in two steps. First, I will try to infer the magnitude of this vector, and secondly, I'm going to get the direction of this vector. Yes, after all, this whole thing is a vector, right? This is a vector. So if I know the magnitude, if I know the direction, I know what that vector is all about. So currently I am focusing only on the magnitude of this vector. Now, to get this magnitude, let us now focus on the figures, the diagrams that I have made here. So this is the trajectory of the particle. This is at current location at time t, and at time t the local tangent is pointing in this direction. This is et. Then at time t plus delta t, the particle comes here. During that time it has followed this trajectory, and that small part of its trajectory must have a length of delta s. Now at this location, when the particle reaches this location, the local tangent has changed its direction somehow. Somewhat it has changed its direction. This is the direction of the local tangent at time t plus delta t. Now this is the local center of curvature at time t, right? And thus this entire length must be the local radius of curvature at time t of the trajectory. Now if we go ahead and connect C with the particle location at the next time instant, I get this line segment. There must be a small change in angle between, in other words, there must be a small angle subtended by these two line segments, this and this. We denote that by delta theta. This is a small angular increment. Now these two unit vectors, et at time t and et at t plus delta t, both have magnitudes. They have their magnitudes as unity, but their directions are not the same. However, it is possible to displace this vector in a way that I do not change its direction, but I only take its tail, which is here, and make it coincide with the tail of the unit vector et at time t. Should always be possible, right? I'm just taking the tail of the vector and placing it right on the tail of the other vector. The vectors will remain unchanged. That is what I'm showing here in this diagram. So this vector is et at time t, and this vector is et at time t plus delta t. Now it turns out that the angle between these two vectors, when their tails have been placed on top of each other, will be the same delta theta that you see here in this diagram. Now, having placed the two unit vectors in this manner such that their tails coincide, I am going to claim that with their tails, with the point where their tails are coinciding, taking that point as the center, we can draw a circle of unit radius such that the heads of the two unit vectors will lie on that circle. Remember, both unit vectors have one magnitude as 1, and thus if their tails are coinciding, you can always draw a circle of unit radius such that their heads of the two vectors will lie on that circle. That's what I'm showing here. Now let's look at this quantity. Et at t plus delta t minus Et at t. This quantity, which I have written here also, I am using the symbol delta Et. This is a vector which is the difference between the Et vectors at two time instants. I am representing that by delta Et. And then I also put delta S in the denominator and it becomes delta Et by delta S. Now look at this figure again. This figure. When delta theta is finite, this line, maybe I use a different color. Actually, it's already shown here in green color. You will see that this green arrow, it actually represents this delta Et, right? The arrow with its tail here and its head ending at this point. This is what delta Et is. Now when delta theta is small, when delta theta is finite, this magnitude of this vector, what I am showing with blue color here, will be somewhat different from this arc length. Somewhat different from the arc length. However, when delta theta goes to 0, it is reasonable to expect that the length of this unit vector will become more and more close to this arc length, right? But then what is this arc length? This arc length must be delta theta times 1, right? 1 is the unit, the circle has a unit radius and this angle is delta theta. So this arc must be delta theta. So my claim is that delta Et in the limit delta S going to 0 will become nothing but delta theta itself. Now let's go back here. Rather here. Okay. So I'm saying that in the limit delta S going to 0, this quantity will become more like 1 times delta theta, and in the same limit delta S will also become a function of delta theta. And to find what function that would be, I go back to this figure. Now look at this figure. Here delta S is this arc. This is delta S. Isn't this delta S equal to rho times delta t times delta theta? That's what I am writing here. So my overall conclusion is that this whole thing in the limit of delta S going to 0 becomes delta theta by rho delta theta, which is 1 by rho itself. Thus, the magnitude of this vector in the limit, the magnitude of this vector must be 1 by rho. That's all. That's the conclusion I have. Now the next question is, what should be the direction of this vector? One part I have already obtained. Now let's work on finding what should be the direction of this vector. Okay. Again, I am going to appeal to the geometries, the geometric details that I have on this slide, this figure and this figure, to infer the direction. My claim is that in this limit, when delta S goes to 0, the direction of this whole thing will be nothing but the direction of delta Et itself. right? Delta Et itself. Again, we have a vector in the numerator, a scalar in the denominator. So the direction of this whole thing will depend on the direction of the numerator itself. So we have to see what would be the direction of this quantity in the limit delta s going to 0. We go back to this figure. This is my delta Et. In the limit delta s going to 0, this vector will become more and more perpendicular to this vector, right? And this vector is nothing but Et at t itself. So my conclusion is that the direction of this vector will tend to become perpendicular to Et, and it must be pointing, I'm taking you back here, as delta Et becomes, as delta s goes to 0, the direction of this delta Et vector will tend to become perpendicular to this Et local tangent vector, and it must point in the direction of the center of curvature. So delta Et should be like this in the limit delta s going to be 0. But then we realize that this direction, which is perpendicular to Et and pointing towards C, must be the En vector itself, the normal unit vector. That brings me back here that in the limiting value delta s going to 0, the direction of this entire vector will be equal to En. Okay, so by this time I have enough information to confidently write the expression for this vector det dsf. This must be what I have written here. This vector is along En, and its magnitude is 1 by rho. So going back to the expression of APF, I had processed things till this point 2 slides ago, and now I have an expression for this. I have processed things till this point actually, and I was looking for some information about this vector. Now I know that this vector is En by rho. Once you plug that in here, you get the expression of APF in the path coordinate system. So APF in path coordinate system has two scalar components. One is s double dot, that is acts along Et. The other is s dot square by rho, and it acts along En. Here I have, for illustration, I have considered a trajectory which is something like this. If the particle is at this location, then the particle must be having an acceleration component along Et. This is the direction of Et. Particle is moving from left to right. So there is a component of acceleration as double dot in Et direction, and then there must be a component of acceleration along En direction, and that component will have magnitude s dot square by rho. At a later time instant, when the particle is here, it must be having an acceleration which is s double dot Et in the tangential direction, and then another component of acceleration s dot square by rho along En direction, which in this case will be pointing upwards. Here En was pointing downwards, as seen by this man. So I want to summarize what various expressions, various final expressions that we derived in today's class and even in the previous class. What I am showing here is, in this column I have I am writing here frame fixed Cartesian coordinate system. Here we have cylindrical polar coordinate system, and this is the path coordinate system. If you want the expression of VPF, this is what we obtained. If your working coordinate system is frame fixed Cartesian, this is what we obtained for the same vector when you have cylindrical polar coordinate system, and this is what we obtained today when we use the path coordinate system as our working coordinate system. Expression for APF in a frame fixed Cartesian coordinate system, the simplest expression that we can have for a general three-dimensional motion of a particle. If you choose to work with cylindrical polar coordinate system, you have this expression, scalar components along ER, E phi and EZ. And finally, if you have path coordinate system, then this is the expression that we obtained just a couple of minutes ago. These expressions will prove very handy when we try to solve problems of practical interest, and then at that time we will have to make this judgment ourselves which coordinate system would be better for us. Now once you have one of these coordinate systems as your preferred working coordinate system, you will realize that you may have to express many other vectors in your working coordinate system. Of course, we derived expression for two vectors of immense importance. One is VPF, the other is APF. Those are very important kinematic vectors. But then we would also need to express some other vectors in our working coordinate system. Vectors like force itself or angular momentum of a body and or some other vector. So it is if you commit, if you have chosen one particular type of coordinate system for your problem solving, then you may end up having to express other vectors also in your working coordinate system. So if you are using a frame fixed Cartesian coordinate system, then you would express any arbitrary vector as what I have written here, where E1, E2, E3 are frame embedded, and then we know that these are scalar components of vector A along E1, E2 and E3 in the Cartesian coordinate system. we are familiar with this idea. If your working coordinate system is cylindrical polar, then you would like to express vector A as this: a scalar component multiplied by ER, another scalar component multiplied by E phi, another one multiplied by Ez. On the other hand, if your chosen coordinate system is path coordinate system, then your vector A will be expressed as a scalar component multiplied by the tangent unit vector, another scalar component multiplied by the normal unit vector, and yet another scalar component AB multiplied by the binormal unit vector. Now, in some books, in literature, and as we talk about various scalar components of vectors, there are some phrases, descriptive phrases for the scalar components of a vector in cylindrical polar coordinate system. It is good to be familiar with those phrases. AR is also called the radial component of A, vector A. A phi is called the circumferential component of A, and AZ is called the axial component of A. In context of the path coordinate system, AT is called the tangential component of A, AN is called the normal component of A, and AB is called the binormal component of A. Now, sometimes in real life situations or while solving some practice problems, we are interested in finding the local radius of curvature of the particle trajectory when the velocity and acceleration are known. If you refer to this diagram, we have the particle of interest located here at this point. Somehow we know the velocity of the particle, say it is VPF, and we also know the acceleration of the particle APF. And we may be interested to find the local radius of curvature. There is a useful relationship which I have presented here. The local radius of curvature can be expressed in terms of VPF and APF in this manner. The derivation of this I have included here. This expression is general in the sense that rho is a scalar, and you see that the quantities that are appearing on the right hand side are some operations which have been performed on vectors. So this expression itself is coordinate system independent. However, this relationship can readily be proved using the expressions of VPF and APF that we obtained using the path coordinate system. So if you take VPF to be S dot ET, APF to be what we derived 10 minutes ago, if you take these two terms and put on the right hand side, you will end up having rho as the only surviving term. This is how we derive. The full derivation is on the slide. Anybody wants to read the derivation, you can pause the video and read the details. But this is the expression, and with this expression I would like to move on to the next slide. The next slide is also about finding the local radius of curvature of a particle under certain condition. The condition is that, so this can be considered as a special case. Mind you, this expression, what I presented on this slide, this is general. For a general three-dimensional motion, this is true. The next expression that I am going to derive for rho is applicable only for those cases in which the particle is following a trajectory which is completely confined in one single plane. Further, we assume that the trajectory of the particle is known. The trajectory of the particle is of this form, f of x is known. So if you look at this figure on the right hand side of the slide, I am showing a frame fixed Cartesian coordinate system. The unit vectors are I and j, and I and j are fixed in f. This is the trajectory of the particle. We know the equation of this curve. This is the current location of the particle. What my interest is to find out what is the radius of curvature. So this is the local center of curvature of the particle at this time instant, and I want to know rho. So this derivation is about finding local radius of curvature under these conditions what I have mentioned. I would like to go to the next slide directly and show you the expression. This is what the intended expression is. So if you know the trajectory f of x, then using the first and second derivative of the trajectory, you can ascertain the local radius of curvature. Here f single prime means first derivative of f with respect to x, and f double prime means the second derivative of the function x with respect to x. So with the known trajectory information, one can find the local radius of curvature, applicable only for planar motion. Please keep this in mind. Well, I have the full derivation here on this slide. Again, anybody wants to look at the full derivation, you need to pause the video and you can read and understand all the details that are given here. I am skipping this part as far as my commentary on this slide is concerned. VPF, then we find APF, we take a cross product of VPF and APF, and then we go back to the same expression that we had earlier. This is what we derived. The last derivation is you put VPF, APF here and take the cross product. You will end up expressing rho in terms of the first and second derivatives of the trajectory.